we need to consider when constructing a network. So my name is Garth Lowe, and I'm a network engineer working in the customer service group. So that's CSG for short. So CSG provides support to our engineers and salespeople around the world. In terms of where we fit in is we're offering support, and Allied Telesis, we offer a very flat support structure. And this provides our country engineers and salespeople easy access to expertise, and also really shortens the resolution times. In terms of how it all fits in, we've got our salespeople, or country engineers and salespeople, and they can directly talk to our APAC TAC team. So APAC TAC is our Asia Pacific Technical Assistance Centre, and they provide support solely to our APAC engineers and salespeople. So APAC TAC and CSG, we work very closely together. We sit in the same building, we actually sit in the same floor, we work side by side. So you can think of APAC TAC and CSG as almost one group. In the same building, we have all our software developers. And our software developers, they're working on our operating system. So this is the networking operating system that runs on our devices. So here in APAC TAC and CSG, we can talk to the developers directly. We can just take a walk up and then talk to the appropriate developer. So the developers all specialize in various different protocols. So we'll have like a bunch of developers, they'll be working on OSPF, some may be working on RIP, RSTP, and other features. So throughout this webinar, feel free to ask any questions. Just ask in the Q&A chat bubble on your Zoom, and we will try to answer your questions the best we can. And hopefully this webinar should be around 45 minutes, but I haven't timed it, so it may be over, maybe under. We'll soon find out. So just let me start with a brief rundown on Allied Telesis, who we are, our offices, and what we do. So Allied Telesis was founded in 1987. We have been serving the needs of our network communication industry for over 30 years, focusing on connecting people through networking. Our headquarters is in Tokyo, Japan. We have over 3,000 employees in 56 locations worldwide. We have 7 R&D centers, and we own 3 manufacturing factories in China and Singapore. Our overseas these operations of these factories, from production line to sales and support, including precise product control. This means we're committed to provide our customers with products designed and built to the highest standards and quality. We provide everything from product planning to development, from development to manufacturing, and from manufacturing to evaluation and world-class professional support. Allied Wear Plus, Vista Manager and AMF, our AWC Smart Connect and Channel Blanket, all this works together as an extremely powerful network monitoring and management, connecting the world securely and safely. Our world is increasing in complexity. Our goal is to make complex networking simple, secure, cost-effective, and manageable. Today, more than any other time, you need a technology partner that has both the vision and the capability to take your network communications to where you need them to be. So the agenda for today's webinar is broken down into 4 parts. Network partitioning, network redundancy, traffic control, and security. And all these four topics, they sort of fall into this foundation of things you need to consider when building a network. So we've broken it down into four things. So network partitioning. So we want to break the network into smaller parts, and this is to reduce the broadcast domains. We want to have some network redundancy built into the network. So this means that if a device should fail or a link should fail, users still have connectivity to where they need to go. For instance, here we've got this device, 3 device that goes down. The user still has network connectivity via a different path. The third thing that we want to consider is traffic control. We want to make sure that certain types of traffic get through the network at a higher priority than other traffic. Traffic like voice, for instance, where it's time sensitive, we need to ensure that traffic gets through first before other traffic, such as maybe email or maybe word processing traffic when you're saving. The fourth thing that we should consider is network security. So within network security, there are a number of subtopics. One of the sort of subtopics is we want to make sure that authorized users can access the network and unauthorized access users are denied access into the network. So this webinar will be covering all these four topics in a little bit more detail. So the first consideration is network partitioning, or in other words, VLANs. So basically a VLAN is, we take a bunch of ports and we group them together. And these groups can't see one another. So for instance, in this right-hand example here, we've separated the switch into 2 groups or 2 VLANs. It means that these devices over on this side, they can't talk to these devices over on this side. So the reason why we want to do this, well, there's a couple of reasons. One, it may be beneficial to logically divide the network into different areas. You could have, say, for instance, your sales department in one group, your marketing in another group. But one of the primary reasons is to reduce the broadcast domain. And over here, we've got an example of a broadcast domain. So when A transmits a packet, and by this broadcast domain, we're talking about a layer 2 broadcast domain. So we're talking about Ethernet. So when A transmits a packet into the switch, this broadcast packet is an Ethernet packet with 4 Fs. This packet will be transmitted to every single device within that broadcast domain. So in this case here, it's not too bad. There's only 4 devices. But if this broadcast domain was very large, maybe thousands of devices, that means that one device will be receiving maybe thousands of broadcasts. And the thing with a broadcast is it needs to be processed by the CPU because it's a broadcast destined for every device. So it can load up the CPU in terms of a PC. PC is quite powerful these days, so you may see the PC just going a little bit slow. But for devices with sort of a less powerful CPU, such as a wireless AP or maybe a CCTV camera or even the switch, an excessive amount of broadcast can actually bring down the device or make the device unusable. Hence the reason why we want to sort of break the network into different parts is to reduce the broadcast domain. So we can see here A transmits a broadcast, C and D won't get the broadcast because they're in a different VLAN, and only B will receive it. So we'll just have a look at different technologies within the VLAN. So first of all, there are different types of VLANs, but we're just talking about port-based VLANs. So port-based VLANs are the most common type of VLANs in use. That's where we, take a number of ports and put those ports into a group or a VLAN. We've got other types of VLANs such as MAC-based VLANs and protocol-based VLANs. So one of the problems with port-based VLANs is if you want to connect two switches together, and both these switches have multiple VLANs in them. So to connect the VLANs between the switches, you need to dedicate a port in each of the VLANs, like so. So for this top switch to talk to this bottom switch, we need to have a port in this VLAN 1, and we need to have in VLAN 2 a port connected into VLAN 2. So as you can see, it's a little bit of a waste of resources because we need to have two connections between the switches. So if we just jump over to this diagram over here, it's a little bit congested, but what we can do is we can have this thing called a port-based VLAN. And with a port-based VLAN, we can use one link, and what we can do is we can tag packets going over that link, and we can tag it with the VLAN that the packet belongs to. So for instance, this orange VLAN down here, when it sends a packet out, it'll send it out to the switch will send it over the tag port. When it sends it over the tag port, it will put a tag or a header on the packet and say, okay, I am a member of this VLAN orange. So when this receiving switch receives the packet, it'll read in the tag, note it's for the orange VLAN, and it'll only send it out the orange ports. So this way here, we can save the number of connections between two devices. This this middle one is multiple VLANs, or in other words, private VLANs. And it's kind of a special way of setting up VLANs. What it allows us to do is it allows us to have a number of users, and they all share the same uplink. So they can all talk to the servers or talk out to the internet, but what they can't do is talk between one another. So it's a special type of VLANs. A lot of times implemented in wireless setups, where you don't want wireless people or devices talking between each other. So we have a couple of, we offer a number of different types of switches. These are a couple of our edge switches. We've got the AT230 and the GS950. So they support a number of different features. The difference between is the two is the X230's just got a bigger, has a wider range of features than the GS950. So they all can do, they're managed by the web, a bunch, you can configure VLANs, link aggregation, and they're both are fanless. So the second consideration we need to think of when we're building a network is network redundancy. We don't want a failure within the network to actually bring down the entire network. We want the network to continue operating. So within network redundancy, we've got different aspects we want to look at. So we've got link redundancy, path redundancy, core redundancy, power redundancy, and out on the WAN redundancy. So for link redundancy, what we want to avoid is when there's only one link between a switch, is if that one link should fail, then that connection between those two devices will actually go down. So with link redundancy, we want to avoid that. So in the past, what we could have done is we could have cabled two links between the device and had one link as the active device and one link as the standby device. So that means when users want to communicate upstream, that all go over this active link. So in the event of a failure, the active link fails, and the standby link then becomes the active link. And then users will start using this active link. So what we can see here is kind of an inefficient use of resources because we've got one link that's not actually used, and it's just as a standby. And all the users have to go over this one link here. So with link aggregation, what this allows us to do is it allows us to take all those links and bundle them together to create one big link. So in this case here, we've got 5 links, 1, 2, 3, 4, 5. They're all running at 1 gig. So now we've got a 5 gig link and just also one 5 gig link. So the additional advantage of this is also it provides us a little bit of redundancy too. So if one of those links should fail, we've still got the other links taking control. The other thing to note about link aggregation is all the links are active. So users, one user could go over one link, another user could go over another link, another user could go over another link. So with link aggregation too, so if you could have actually up to 4 links that fail in this example, and you've still got connectivity between the two devices. So the other consideration we need to think about in redundancy is path redundancy, and we're looking at it in a loop topology. So in a loop topology, by default, physically, there will be a redundant path just by the nature of it being a loop. It means that traffic could go one way or could go another way, this way here. But loops are bad in the network. If you've got a loop in the network, it will bring down the network almost immediately. So to avoid loops, what we need to do in this physical loop topology, we need to put a loop protocol on it, and this will avoid, or this will stop the loops. It will detect the loop and stop the loop. So one loop protocol that we can use is spanning tree protocol. So spanning tree protocol will detect the loop in the network, and it will just block one of the ports. In this case, it's block this port here. So with path redundancy is, so the normal path, if we're going from this switch over to this switch, it may have been, it would have to go through this way because this port's blocked here. If the link should go down, for whatever reason, spanning tree will detect that the loop has gone down. It will then unblock this port, and then the flow of information, or the path, will now go via this L3 switch, and it'll go over this redundant path. So the thing with spanning tree protocol, it is rather slow. It can take up to 30 seconds for it to detect this link has gone down and then to unblock this port. The newer iteration, rapid spanning tree, sort of drops this time dramatically down from 30 seconds, typically down to sub 1 second. But 1 second is still quite a long time in networking terms. The other disadvantage of spanning tree is you can only have 8 hops. So in other words, you could only have typically 8 devices forming a ring. So EPS or Ethernet protected switch ring is another loop protocol that we can put over a physical loop. So it works well, the same as spanning tree, is it detects the loop and it will block the loop. It does it in a different manner. So what we've got is a master switch, and we've got a number of transit switches. So what the master switch will do is it will send out a health message, and this health message will traverse the switch until it comes back to itself on the secondary port. At that stage, the master knows that the loop or ring is complete and will block this particular port. So when this link here goes down, what will happen is both these switches will send a packet to the master switch to say this link has gone down. And what the master switch will do is will unblock this particular secondary port. So the flow of information can go via this redundant path. So the thing about EPSR is it's very quick. So we can get times as quick as 50 milliseconds cut over. And the other thing also is you've got unlimited hops. So this size of this ring can be as large as you want. So just another thing to note. So we do have another ring topology or ring protocol called G.808032, which is a standard space loop protocol. Whereas EPSR is it's more of a allied Telesis protocol. So we'll just look at the core redundancy. So typically, what we want to avoid is if there's an outage or failure in the core, we don't want that to bring down the network, because in the core, you typically have your connection maybe out to your internet or your WAN, and you have your servers all connected into your core typically. So there's different ways of implementing this. In the past, it used to be a combination of protocols that we had to use to achieve core redundancy. So what we did in the past was we had 2 devices, an active device and a standby device. And these 2 devices were running a protocol called VRRP. So what VRRP allows us to do is allows us to share an IP address with the active device owning that IP address initially. So what would happen is a user would come in, they had a gateway address of the IP address that's been shared. Because it's active, or because the active one is owning the IP address, the packet would go to the active device, and the active device would then send it out to wherever it needs to go. So when the active device fails, the standby device takes over that IP address and will respond to that IP address. So that means users would then go via the standby device and then access the servers and whatnot. And to avoid loops, or you can see down here, we've got spanning tree too, because we want to have sort of link redundancy down here. And this could be the distribution or edge layer. So each of these are running its own broadcast domain, so, or Ethernet segment. So it's a bit hard to tell, but on this device here, you've got a loop from going from there and then over this common link and then back here. So you've got a loop, so spanning tree will block one of those ports. So these days, we don't have to worry about configuring VRRP, configuring spanning tree, because it did take a little bit of time to get your head around and understand how it's all working. What we can use nowadays is virtual chassis stacking. So very simply, it allows us to join two switches together to form one virtual device. When you log into the device, you see it as one unit. So both units are in use. So it means that what we can do out on the distribution or edge is we can then form a link aggregation. A link aggregation can go to both of the two switches because they're acting as one unit. And what that means is you can increase the bandwidth to your edge or distribution switch, and packets can go both ways. And it doesn't matter if there's a failure, because there will be a redundant path. So if this device here should fail, you've still got this path here. If one of the links should fail, you've still got the other links in the link aggregation. So on our sort of important devices, we want to have power redundancy. So if something happens to one power supply, we've still got power to the device. In the past, we used to supply power with an external power supply, so it's an extra unit that then connected into the device. These days, on our sort of core devices or important devices, they've actually got two power supplies built in. And the device only requires one of these power supplies to actually work. So WAN redundancy, there's a couple of different topics here. So first of all, we want to provide some, obviously WAN redundancy. So what we could have is have two WAN links. One could be a primary link and one could be a failover link. So when the primary link fails, then the backup link takes over. What we could do is we could configure load balancing. So that means both these links are active and traffic will be load balanced over both of the links. And it also takes into consideration, if one link is faster than the other, then more traffic will go over the faster link. We can also build in device redundancy into our WAN devices. So a lot of the times these days, we only have one connection out to the WAN or internet. And the reason behind that is usually that one connection is quite expensive. So to have another link might be cost prohibited, and we just can't afford it. So what we can do in this case here is have two devices and connect the two devices with a bypass port. And what the bypass port does is operating at layer 1, which is the physical layer. So all it does at a layer 1 level is just connect this bypass port directly into the WAN port. So from the WAN point of view, it's either connecting straight to this switch over here. So I'll just explain how this actually works. So these two devices here are running VRRP, so they're sharing an IP address. This master switch here owns the IP address. So packets coming in will be sent to the master. The master will then just send the packet out the bypass port And because it's a layer 1 connection, it will then just forward it out this WAN port here. So what that means, because it's a layer 1 connection, if this device here should fail, it won't matter because it's still a layer 1 connection. It will still have a connection here. So in other words, this device could fail, could have no power or something like that, but the bypass port will still connect to the WAN port. And obviously, if the master should fail, then VRRP kicks over. This takes over the IP address, and then it will just use the WAN port. So we have a range of sort of higher end switches. So these switches here are designed to either go into your core, into your distribution. So we've got an X950. This is sort of our latest switch. Our X930 is sort of an older switch. It's been around for a number of years. So the third thing that we need to consider when building a network is traffic control. And this is broken into two parts, QoS and hardware packet filter. So very simply, QoS allows us to control traffic and basically who has priority in the network. In this example here, we've got, without any QoS, we've got IP phone and just a PC. They're sending over this common link here. So when this common link becomes congested without any QoS, what will happen is the this device here will just start dropping packets. And if it starts dropping voice packets, then voice calls will start to be degraded. So with QoS, what it allows us to do is it allows us to prioritize these voice packets. So they're actually transmitted first, and then the packets from the laptop, they'll have to wait behind the voice packets and then be sent. And when the link becomes congested, it will be the data packets from the PC that will be dropped first. So how does the switch do this? So it does it through a thing called strict priority queuing. So what happens in the switch is a switch has got a number of queues, and these queues fill up with data. So what happens is when the phone transmits data, it gets put into a very high priority queue. So in this case here, it's Q3. So there's the other devices, they get put into a lower priority queue. So orange packets get put into a queue of 0, and these green packets get put into a queue of 2. So now when the switch is sending the packets out, it will try and empty out all the packets in Q3 first. So it will send out the pink packets first. When there's nothing in the top queue, Q3, we'll start emptying out packets in the second queue. So then we'll see some green packets being sent. And when there's nothing in these top 3 queues, then traffic in the lowest queue, Q0, is sent out. So in this way, voice traffic always gets sent out first. QoS also allows us to assign bandwidth to applications or queues. So in this case here, Q3 or audio traffic, that can use up to 20% of the bandwidth. What this means is voice traffic if we've got a lot of voice traffic, can't consume all the bandwidth. It can consume up to 20% of the bandwidth. And then likewise, the screen traffic or the key operations data, it is allowed 50% of the bandwidth, and then the other traffic, we can allow 30% of the bandwidth. So the other way we can control packets in a network is via packet filtering. And packet filtering occurs on the ASIC, which is the silicon. So there's a network chip on the switch, and that allows us to switch or route packets in hardware, so very, very quickly. So the packet filter is actually implemented on the ASIC, so very quick, so it's at hardware speed, so there's no delay. The packet filter, or hardware packet filter, very simple concept, is an access control list or ACL list, and this just contains a number of entries. And there's and these entries will have basically a criteria, and if the packet matches that criteria, then the packet will either be denied or permitted. So the matching criteria could be one of these 4 things. It could be a source destination MAC address, source destination port address, or source destination IP address, or a particular type of protocol, for instance. So it's quite simple. So a packet would come in maybe from MAC address B. In the access list, there might be an entry saying allow, so MAC address B, permit. So when the packet comes in, it gets matched up and it'll allow permit. If there's an entry deny MAC address C, packet comes in from MAC address C, they'll match the entry and it will be denied or discarded. So the last thing that we want to consider is network security. So network security is huge. There's a lot to network security. So I'll just go through. So this is quite a good slide because it sort of breaks down the different parts of network security. So first of all, we want to make sure that only proper users have access to the network, and other users or non-valid or unauthenticated users haven't got access into the network. We want the network to be protected against external sources such as viruses and malware, etc. When we're communicating between 2 devices over an unsecure network, we want to make sure that if the traffic is intercepted, the external source or the traffic is just useless to the external source. So the external source can't actually decipher the traffic at all. And this one down here is we want to make sure, or we want to avoid the situation where there's an internal source that has an external threat. So it may be malicious or non-malicious, but we may have a user introducing some sort of virus. So we want to protect against that. So the first one was we want to make sure that only valid users can connect into the network, and we can do that. So a few mechanisms. There's the 802.1x authentication, MAC authentication, and web authentication. I'll just go through these very, very quickly. So with 802.1x authentication, the user provides either a username or password, or a digital certificate, or even a VID. So what happens is they provide their credentials. The switch will then forward their credentials off to a radius server. The radius server will look up to see if they're a valid user. If they, well, they'll send back the response to the switch, which is called the authenticator. And based on whether they are a valid user or not valid user, it will allow either the user access, or if it's an unauthorized user, it will just block the port. MAC authentication works similar, except for the user doesn't have to provide any particular username or password or digital certificate. All it has to do is start transmitting packets. So, and we're talking about MAC is Ethernet, so every device has got a unique MAC address. So again, what happens is the switch will then forward that on to the radius server. The radius server will check that the MAC address is valid or not valid, or send a response back. If it's a valid MAC address, it will allow the user through. If it's an invalid MAC address, it will just block the user. And the third way of authenticating a user is through web authentication. So what the user will receive on their screen is through their browser, typically, is a sort of a login and password screen. So what the user will do is he'll fill out his username, password, type it in, and then again, they'll be sent to the radius server. The radius server will then either authenticate or will authenticate the user. If it's valid or not valid, it will allow the user through or not allow the user through. So a firewall basically controls the flow of packets between a trusted network and an untrusted network. So this is normally put in your connection between the LAN and WAN. So again, typically quite simple. So usually the firewall has a number of firewall rules, and the firewall rules basically will either say allow the packet through or deny the packet, basically. And the firewall, well, traditional firewalls used to work at layer 3 and layer 4. So it'd work at the IP layer and the TCP or UDP layer. So it'd say, okay, allow this IP address through or disallow this IP address, or allow this particular UDP or TCP port number through. Newer generation firewalls can actually inspect the packet and work out the actual application. So you could have firewall rules to say, allow, I don't know, allow Google through, but don't allow YouTube through. So UTM, or Unified Threat Management, basically this is sort of consolidates sort of security functions into one application to protect the network. And typically the UTM is operating on all the layers right up from level 2 right up to level 7. So it can actually inspect the contents of the packet. And then based on the contents of the packet, so it can detect, if there's a virus or malware, and it can detect other things too. So it really looks at the entire packet to determine whether that packet is a threat or not. And if it is a threat, then it can sort of drop that packet. So the fourth type is VPN. So basically, simple concept, if we're going over an insecure network, we don't want the data to be unencrypted. If it's unencrypted, it could be intercepted, deciphered, and there may be passwords or sort of information that you don't want to get out. So when we're sending information over encrypted, over a unsecure network, what we want to do is make sure that that data is encrypted. So if someone does intercept and views those packets, it just doesn't make sense. So what we've done is we've had a look at making sure that users, the proper users, have access into the network. Threats are discovered and dropped. And in this case here, when we use a VPN, we ensure that even if the data is intercepted, it doesn't mean a lot. So the third, or the last one, is internal threats. So an internal threat can be accidental or intentional. So what we've got here is we've got a user here. So unknown to him, he's introduced a virus or some malware onto the network, and this is then propagated to other users. So he might have done this unintentionally. He might have just bought in a USB stick or downloaded something that's got is a threat. So by the time that it's discovered, it's actually been propagated to other users. So with our solution, AMF Security or AMF Sec, what it allows us to do is it allows us to control the network. So if a threat is introduced, it's detected by a security device. It could be a firewall or any other security device. And then that communicates to what's called the controller. And the controller can then program the network to disable the threat. So in this case here, it's disabled the port. So that means that the virus can no longer transmit itself through the network. So there's a number of aspects to the IPsec security. So basically, it all uses this AMF Sec controller. So the firewall security device can talk to the IPsec controller, and then the controller can then reprogram the network. And it can do it two ways. It can do it via AMF, using the AMF protocol, or it can program the devices through OpenFlow. And like in the previous example, the AMF Sec controller, in this case, will disable one of the ports. So we have a number of, or a couple of sort of UT and VPN routers. So we've got our AR4050S and AR3050S. So these are basically the same devices. The only difference is the AR4050, it's just got a sort of a higher, it's got more capability. So it's got a better CPU, it's got more RAM, etc. So that was sort of a very quick introduction to a lot of technology. So hopefully it's made sense to you. But this is the end of the webinar. So I'll hand you back over to Aki, and you can carry on.
Okay, thank you very much, guys, for your presentation. Before we move on to a Q&A session, I'd like to ask for a survey. As you can see on the screen, the QR code, can you please scan the QR code, and then the survey page is coming. We would like to improve our service. So please help to fill in the survey. There are only 2 questions, very simple. So could you please scan the QR code and then the URL is coming. Could you please help to fill in the survey? We would like to improve our service. And this is the end of the slides. Q&A, next is the Q&A session. But Q&A usually takes some time. So if you want to leave this webinar, you can leave now. Again, Q&A session usually takes some time. So if you want to leave this webinar, you can leave now. Thank you very much for your time. We provide this kind of webinar Monday, Wednesday, Friday regularly. So if you haven't registered and you're still interested in, please register the webinar. Tomorrow, follow-up email is coming to you. And in the email, there are URL for the registration for other course. So if you haven't registered, could you please register? Thank you very much for your time. So now let's move on to the Q&A session. If you have any question, could you please type your question into Q&A window? You can see a Q&A window on your screen. So if you have any question, could you please type your question into Q&A window? But if still you would like to speak, could you please raise your hand? You can see on your screen raise hands button. So if you'd like to speak, could you please raise your hand? But basically, if you have any question, could you please type your question into Q&A window? It's much better and much easier for us to manage your question. Thank you very much.